Hello and welcome to today's Wolfram Institute live stream. Today we have Steve Liu, a first-year undergraduate at University of Southern California, studying math and electrical engineering. Today he'll be presenting his project from the Wolfram Summer School this past summer on the Collatz conjecture. Steve, go ahead.
Thank you. So thanks for the, I'm very grateful for this opportunity to be given to explore such an interesting math problem. During my time at WSS, I was able to take on this project about a generalized form of Collatz and explore it further. And basically the aim for this project is to find the most statistically balanced, aka the most neutral ones, where it's like in the statistical sense, the bias is closest to zero or it doesn't like go up or down in the other sense. So basically, it would also be a more theoretically hardest to prove one due to its like non-convergent and non-divergent nature. So I mean, yeah, based on all my explorations, there doesn't seem to be a definite one, but there's a lot of interesting discoveries that I made that I definitely want to show today. So first of all, this project was directly inspired by one of Stephen's posts where he talks about some of the he talks about the tag function. He also briefly mentions the more generalized version of the Collatz. The specific one he explored is let me try and find it. It's let me see. This specific one is a mod 3 one. It's this one. Basically, it has the following coefficients where for the first one, it's basically, it detects like, it's like one, like basically that's like division by three. This is division by three. This is 4n plus two, and this is 7n plus one. Basically what happens is that this is, instead of like a standard Collatz where you have two conditions, one for a division and one for increasing addition, which is an increasing way, we have three instead. So there's a bit more variety of how much it can increase and how much it can decrease. Basically, we started with this plot, and this plot basically explains the convergence based on the numbers. So let's say we have a number that's let's see, that's like 1 to like about like 1,000. Basically, these will correspond to the percentile of the numbers. So if you have the first percent, which is 10%, that'll be like 1 to 100 or something. So it's like more organized with percentile. Um, in order to also like further reduce computational like strain on this, because it's pretty expensive and we're exploring a lot of numbers, basically I use some kind of like randomly selected choice within this group. So to represent the graph you see here. Now, and
Okay,
basically
hold
interestingly,
on.
the one
For the sake of our audience, can you explain the original Collatz problem as a
oh
um,
sure, I forgot about that, sorry. Basically the original Collatz looks something like this. Basically the initial one stated that for anything that's like even, you divide by two. And for anything that's like odd, you do 3n plus one. Now, to further derive this, since like if it's even, it's obviously going to continuously like divide and then, so basically we can also like write it in this form. Sorry.
okay, yeah, so it's frac n over 2, I guess, if n is
How
if
do
n
I
is
fix
even.
this? There we go. So basically, you can also like put the other term to divide by two to simplify the steps needed. Because if you don't, basically if you do 3n plus one, then later you have to divide again, then that's an additional step. And if you do that just on the step, it's going to reduce the number of computations needed. So yeah, this is the original Collatz. This is written as a simple mathematical function.
Mhm.
Um, yeah, basically I talked about to simplify, we divide by two, and then this ends up being the generalization we have for the original Collatz. There's also a few different ways of actually like computing Collatz. There's one that is using Fractron. Basically, this is like how you generalize it. The issue with Fractron is like it's a bit more complicated and it's not really that intuitive to search for the parameters because that's what I will be doing because I'm going to look through a lot of general Collatz and being able to tweak the parameters like correctly and be able to understand it's like a lot more important. But it's a pretty cool way. you're interested, I have some in my community post. I have links to Russell Martinez basically, and John Conway's like studies. So you guys can like take a look at that. Basically, the generalization I'm going to be using is this, the U function one from Lagrange's research. Basically, it's a more intuitive way of doing it, where you have an n divided by n divided by d and mn minus r divided by d, and it will expand. The terms will expand for each like mod space. So like if you have three, then you will have three terms here. If it's going to be four, there's going to be four terms. So yeah, this is a bit more intuitive and in many ways more similar to the ways that we see Collatz. And this basically allows me to basically tweak the parameters and explore a much greater space of parameters and a lot of variety of Collatz. This is basically the generalization part. But for this specific one, I basically found like uses what Stephen have, because I want to kind of just see like what are some properties of this one and what are like the so that I can compare later on to for other collabs to this one, so I know like if it's more neutral, does it have this kind of trend? So back to what we're talking about before.
Right.
You
So
can
this
see
is
in this
the
graph.
mod 3. Um,
Yeah, this is a mod 3 one
uh-huh.
from Stephen's writing, which
So
I linked over here.
if it's 0 mod 3, if it's divisible by 3, you divide by 3, and if it's mod 1, if it's 1 mod 3, it's 4n plus 2. Is that correct? And if it's 2 mod 3, it's 7n plus 1.
Yeah, that is correct. Like basically you have like three different ways of like going up or down instead of just two in the mod 2 space.
Uh-huh.
And basically we explored a whole bunch of initial conditions and plotted it. Basically each line is the pretty much the average of the percentile. And interestingly, you can see that basically like pretty much all of them do actually converge. Except for maybe this one, but later on we'll show that it also does converge. But you can also see interestingly, like but the convergence, the time of convergence, the steps to do it is basically increasing for each for each percentile. So when you get to the largest one, it actually seemingly diverges for 3,000 step. Now, like, is that actually the case? So I actually computed more, right? I computed like 30,000. And it seems also like I'm computing the top like 10% of values, since like we're only looking for this purple line. Basically what happens is like they do converge, but a lot of them more like as you get towards more to the top, basically it just starts to diverge more, but on the average it still converges. Now, why is that the case? Because we have a lot of these divergent divergent sequences, right? Basically, it's like a mix of both convergent and divergent sequences. So basically, depending on the initial condition you put in, you could actually create like both convergence or divergence, which is interesting, right? That's probably why like according to what Stephen wrote, it is the most neutral one. So
Well,
picking
hold
back
on. So there are. Let's go up to this plot here.
this
The
one,
first one here, yeah. Uh,
this one.
this one. So it looks um, like the orange one from the second to the bottom. Looks like it converges for like a long time, but then like it has some noise later on. Or they're like these
This one?
dotted patterns. No, at the bottom.
Do you mean this one? Oh, these ones?
Yeah, here. I'll try to like. So what's going on there?
Actually, I'm not really entirely sure, but it could either be a limitation of the plotting, or it could be something going on. But I think it might be due to something that's like depending on like the divergent sequences, because they are divergent sequences in these like ranges, even though they're minuscule, they're tiny, which I will show. Like the number of like initial conditions that causes it to diverge is going to be small in these lower spaces, like,
Oh,
but
I
it does
see. Wait.
exist. So
So you started out with like the stuff in the millions here. It looks
I
like
think this is also like log. This is also a log plot, by the way. So it's like not exactly like the
yeah.
values.
But so it looks like it converges, but this could be like oscillating between values still. Um,
Yeah, like because
huh.
I mean, yeah, there's always like a variety of like, different like, convergence like steps between it. So it's like basically it just makes it pretty challenging to do any like like to say absolute for sure that this is basically going to converge or like diverge. But statistically, this is the results, right? So basically, after this, I took it also further. Um, I look at what Stephen provided as an interesting initial condition. Basically this is the smallest route he found. I think that diverges. So basically you basically I tested it. I graphed it for this many steps. And yeah, it pretty much just confirms that it does just like diverge infinitely, right? So
What?
basically,
Well, I mean,
excuse me.
what size of number are you starting out with here?
Basically it started out 469.
Okay.
Actually, yeah. This is basically like what I plotted for Stevens sequence. Um, but like also like interesting to note that given this graph, right, you see like as it goes higher, the value goes higher, the more chances it diverges. Basically because of like these like as the sequence grew, because it's a divergent sequence, it grows like really fast. So as you get to the top, you get a lot of these like really large numbers. And I think that's like one of the reasons why it's contributing to this kind of behavior here. But yeah, we found this, right? But basically, my other thought process is like, since like we have a forward function based on that, there could be also other like, numbers that converges onto this infinitely divergent sequence, right? You have these string of numbers, and as long as one, like any initial condition happens to have a value that exists in this like infinitely like expanding space, then it must be divergent because as it expands onto it, this is just going to be divergent, right? So if we reverse each point on this like sequence on this graph, I would say, then you get a whole web of divergence. So this is basically what I did. I did it for a limited steps because like it's gonna break like the computation is pretty intensive. Especially like for mod 3, instead of only having like two ways of getting this number, you have three ways. So you have this initial way of forwarding, going to increasing to this value. You have other ways from like example, like you might be able to like, okay, I don't think I can zoom in, but on some of them you can see there are intersections. That means that there's like different branches, like basically they can converge onto it. The most I think possibly is definitely gonna be three, because obviously you have only like three ways of like increasing or decreasing, right?
Yeah, yeah.
So
So that's really cool. So you have like this river, and you have like all its tributaries, basically.
yeah, something
Starting
like
from
that. So
469, and
well, I wouldn't say it like absolutely start at 469, but that should be the lowest value you would see. But
yeah,
yeah,
that's where you took like
um,
a random sample.
yeah. Like it's really interesting like how it just like starts it. So this is the graph I made to visualize this. So you can see that this is the red line. This is the line representing this. The infinitely divergent sequence over here.
Hmm.
So it goes, I did plot it for like a really large number actually. I don't actually remember how large it is, but you can see it goes pretty long. But also you can see these branches that plots out now. I don't think I can zoom in on this, but basically like each of this is basically like I mentioned, like a like a different way of getting to this divergent sequence. So you end up having this like entire space. I do also have another graph that labels some of these points. Basically what I found is like a lot of these values are just huge. And so basically like compounding with the observation made here, it just makes a lot more sense that like as the number grew higher and larger, basically you get a lot more of these like numbers within this web. And that would mean that it would be divergent, right? So eventually probably like it will approach to a point where like West approaches like the number approaches infinity, maybe like infinity diverges, but statistically that's not really like likely within the range of numbers we see. But it's really hard to like really have a definite answer for this as well, because like it's like there's a lot of computation need to be needed if like we're doing statistical like analysis on it, and that's like you need a lot of like computation for that. And this is another this is a so to look at the divergence, like the chance of divergence for each percentile, I also made this graph. basically it just shows that like it also kind of shows that how many like values of like divergence are in each percentile like graph, right? And then with this distribution,
Yeah. So what are these numbers saying?
uh these is it a bit too small? Yeah, it might be. So this one's about like this is about 8%, 48, 53, 56, 60, 63, 65, 68, 71, and 76. So as you go higher, it does have this clear trend that like it basically the percentage of divergence is gonna be higher.
As the number gets
Right.
bigger, the likelihood of it diverging in this version of the Collatz is increases.
Yeah, yeah, like as an initial condition, right? So basically like that's also like kind of like what we observed on this graph here. Like the edges are definitely gonna be huge, but like basically when it goes like up to the edges, like they got the as the percentile encompasses these edges, like it's more likely going to diverge because it's more likely going to end up here. And conversely, if you have a smaller number, then it's not likely going to be on here because like literally like if you have like because like 469 is actually the smallest one, so like it's like pretty like sparse from there. And if you look at this like numbers below like literally like 469, there's not going to be any, right? So
Now, is
it's
this
just
for
kind of
like
like
a
a
random sampling of numbers within each of these ranges?
yeah, it's more like a random sampling. Because like the issue is like I'm doing like a huge number. I think that's like about like a million or not a million, but
It's a
like a
hundred
hundred
thousand,
thousand.
yeah. So
It's a
you
hundred
have
thousand,
yeah.
but
So how many
like
numbers
it's
are
like
in
pretty
each of
huge.
these? Is this like a log distribution? Well, I guess it doesn't really matter, but
So
I get the sort of idea that larger numbers are going to have a higher probability of diverging.
yeah. Because like I said, like it's more because like basically like as the sequence grew, more of the large numbers end up here, right? That's like that's kind of like I think the reason why it's doing that. Although like probably more exploration could be done on that because it's not really like a definite answer. This is also another plot. Basically, I think that yeah, this one plot for all of them. It's not a random sample, but it's only doing one to 1,000. And the ones you see here are the the divergent ones. So basically, we're just doing a very small sample of like probably like these spaces here. And you can see this in the entire like 1,000 values, initial values, you have only four that actually goes on this sequence, and all of them are on the initial part, this short section. So, but there are also ones that comes really close to divergent, right? Like for example, 497, this one is really high up here, just like below these ones, and you also get this one. I can't. Okay, yeah, this one's 884. So these two are actually really close to divergent. So there might be some relationship like of like the numbers, that the value, how big the value is, or like the type of value it is. Like is it like even or odd or something like that, or if it's like something related to that that can cause it to have like a seemingly like sort of close to divergent behavior, or like there might be some like relationship that causes it to diverge. But due to like the scope or like in the time limit of like WSS, I wasn't able to like explore that like to the full extent. So
So what
that's
is this plot showing? Uh,
basically it's showing all the numbers from 1 to 1,000, and
but
it's a
what's the
log plot of
y-axis? What's the vertical axis?
the vertical, the
Hmm.
steps, right? If it's like divergent, then it's gonna be on the top because that's the max step you have. Because I'm also limiting to the step, right? I can't just run it for like for how many steps, infinite steps, because you have these divergent sequences, it's not gonna finish.
Oh, wait,
So I
so
do limit it
are
to
you, are you saying that you've run
yeah,
these things for 10 to the 32 steps?
yeah, pretty much. These are the number of steps to convergence, and the ones on the top are obviously going to be divergent ones.
So are you saying that 469 does converge, but only after
Uh,
like 10 to the 30 steps?
no. 469 doesn't diverge. You have this plot. We have this plot here that kind of shows that it
Okay,
doesn't. But
so it doesn't
the one that
converge.
it doesn't. These ones on the top officially doesn't, because yeah, they're also all the ones that's in the 469 sequence, like here, as on the red line. So these ones don't converge. But there's one that's 497 that's like really like it takes a long time to converge. And there's 800, the 884, which also takes a like really long time to converge.
So
So
do
I
they
think that's
converge to the same value or like a particular set of
uh
values?
I didn't actually test for that. I'm just mainly looking for how long they actually would converge. But that could be an interesting thing to explore further. That like we can see like if they do the same value, because this doesn't really show if it's like the same value or not. This is like more of like log and like distribution thing. So that could be something we can do. But yeah, like there's also a kind of interesting like pattern where you can see these kind of like a line here. Obviously, these values would be slightly different, like the steps would be slightly different, but they're within like a pretty close range. You can see there's a range here. There's some values that does converge around 10 to the 16 steps. There's ones that converge around 10 to the 10 steps, and there's a lot more on the bottom here. You do get those some of the outliers here, like those don't really like follow the pattern that well, but it does actually exist within the general range.
Huh. And then so
So
for a
it's
lot of these at the bottom, like there are ones that converge at like 9 steps, it looks like.
yeah, these ones are like 5. Yeah, they converge like pretty like quickly like for these ones. Yeah, so basically it's kind of like a small sample of like the distribution. I mean, if I have a bit more time, I can like probably like increase this to a larger value and run it like overnight and then actually calculate like actually like, have a better like distribution. But again, due to limitation WSS, like I wasn't able to do that. And yeah, I also tried something like with like using like some kind of digital representation. I basically graphed it like this so I can have a clear like view of it. And it sort of looks like a CA actually. So you can see for this rule, you
Yeah,
can
this is
have these
interesting.
ones.
So this is like converting the numbers into a binary and then plotting the
Yeah,
ones and
basically a
zeros.
binary, and then like basically you can see how I plot how I get plot this is like basically using binary, right? So you have one here and one here. And depending on the way you graph it, it actually does kind of look like a CA. You can see that it extends down here, and basically, yeah, it's
Right,
slowly
right.
converging. Basically, this one slowly converges.
Well, so all right, let's look at
So
this. So basically, it's like 1 0 0 0 1 0 0 0 0, and binary is a big number, and it has a lot of
yeah,
zeros at the end. That makes it big, and that also makes it very, very even, right? So it's like
yeah,
every time that there's a white space that it ends in a white space, that means it's even. So it'll like do n/2, and so
hmm
all the values get shifted to the right until you get to these odd numbers here, ending in 1, and then uh, you see some entropy starting to develop in the plot, and then it kind of boils down. Okay, so
yeah.
that's pretty
Eventually
cool.
boils down to the yeah, right. This one had includes the additional one here. Basically, it makes it like it's not even anymore. It's like odd. By the way, this is for like for the ones that people who are kind of confused. This is based. Oh, yeah. This is the specific. These ones are based to Collatz. They're not the ones that Stephen have. That we explored here. Just to clarify. There are ones that down here that we explored that is related to the function up here, but these ones are not. So basically, this is the another one, but I just added a one to the side, and there's a whole lot more entropy here. Basically, what happens is. You can see eventually only converges here. So it's a much stronger process.
Now, is this the standard Collatz where it's 2n plus
This is
3n
standard
plus
Collatz. This is standard
standard
Collatz.
Collatz? Okay.
Yeah. And also note interestingly, like there's like not a whole lot of entropy because basically like for this one, since this is like just even, you have a lot more division until you cannot be divided in. And then you have these ones, and then that's when it started to have these
Yeah.
patterns. But these ones, like for this one, it already have the ones on the side. So basically it just makes it odd and then it starts to exhibit this behavior,
Hmm.
which is actually kind of interesting, but I wasn't really able to like fully understand it. So now this is actually the base tree one. So you can see there's like three colors now. There's like the white, black, and there's like gray here. So
Hmm.
this one, I'm using 2 to the 100 and 2 to the 70 plus 1 for consistency because I want to compare across like, this and this. So this is what I did. Basically you can see that it's a whole lot, cause since it's like, I'm using the base two values, the values in the like initial values is not gonna be exactly like, the two dots on the here. But nevertheless, it's still interesting that like you can see these triangular shapes for me, especially like towards here. Like it's basically all of here is basically zeros apparently,
Right. So
and the
that's where it's
whole lot of ones here.
it's not really increasing in value. It's still like decreasing, but yeah, you have like a
Yeah, it's decreasing,
whatever
but
the
like you
function
can see
is.
it. Yeah, right. But like you get these like lots of like triangular patterns forming.
Oh
So
yeah, I see that. That's interesting.
you can see these two like big triangles. This one's not really that like complete. You have this a little bit of like digits here, but this one's very like standard. Like you see the straight edges and this edges here. This is a base six one actually. This is a basics plot of I think like Collatz. This is the general one, by the way. This is not this is the original Collatz in base six, and this is specific in basics.
Oh,
So
interesting. So this is
actually
sort
took
of um, it's a standard Collatz, but plotted in base six.
yeah, it's just represented differently because I saw Reddit post and I got inspired and then basically I want to see and compare like
Right, right. And
the
I guess yeah, I remember. So they wanted to look at it
yeah
at base six because they had n minus n divided by two versus n times three plus one. So it's like two and three. You
and
want to
six
look at base
basically
six.
is 2 and 3
Yeah, you have some very nice transformations on the bit sequence there for the
yeah
base six representations.
yeah and basically it looks like this is like basically yeah, it does exhibit like a similar, behavior initially to the ones we saw here actually. And but yeah, there's just gonna be a lot more entropy because this is like base six, right? And the representation is a bit different. So we can't really directly compare, but we can still see a bit of like, similarity here. This one is for the specific one we talked about. Uh, I don't really like basically. I think this is a divergent one. I don't think so, but basically, I think I picked a number that actually takes a while to like converge. So
Yeah, I can see it
um
like undulating in value.
yeah. So the issue is like I picked one that's not really like like it clearly shows it converge. So like that's kind of like one of the issues I have with this, but it does actually show the similar behavior as this. But
Can
you can
you
see
can
like
you zoom out on that one so you can kind of see the whole thing?
I don't know.
You can just scale the size of the graphic output.
Oh yeah. No, but I think this is like oh okay.
Yeah.
Yeah, I thought I made it with the pen and that. It still works. Yeah, this is the whole shape.
Uh-huh.
Do you guys want to zoom out on these ones as well?
Sure, sure.
Okay, let me do that. Yeah, it was like more of like I set it to like the width because like it's more like if I publish on like on the community that like it looks a bit better with
Yeah,
the
yeah,
set
that web
like the
format had
color width.
specific, but
Yeah, but this one's is a bit weird because like my screen's pretty wide.
you can.
Yeah, so
All right,
these are the full pictures. This
let's
is
see.
actually kind of long because I'm showing the entire convergence process and
Hmm.
not just cutting it off. So you can see eventually like there's a few dips and then
I
eventually
see. Yeah, at
yeah
the
it
end it
hits.
converges to one there.
Yeah, yeah. This one I think yeah these ones I cut it off because it takes a bit too long to convert and then it basically like looks like this as well.
Hmm.
This is yeah, this is we're seeing that this is like basically issues like it doesn't really like show the click convergence. I mean it is convergent, but it doesn't because the steps is too long. Oh, there's this one. Also try plotting in base 3 actually, because I want to explore different like bases. We have base 2, um, base 6. This is the specific plot in base 3. Yeah, I think the formatting is a bit weird here. So I should probably put this together, but this is the Collatz for base 3. This is the the base 3 the Collatz that we found in Steven's post.
Uh-huh.
And you can see that you have the same behaviors on here, in here. And I think this one also takes a long time to converge, so that's why I cut it off, because or else the image will be too huge.
Right, right. But
This
I
one,
mean, assuming that it might converge. I mean, so what's the story on the specific Collatz function having convergent values?
oh, you mean this?
The
This
yeah,
is this is just like this is the same as like Stevens function. I'm just looking at it in like different like representation here.
right. But for this
So it's
specific starting number, does this one go to a sequence which converges, or does it get bigger?
um I mean I think it does converge, but it takes a while to do since the numbers are decently large.
Yeah.
So it does take a while to do it, but I don't think it actually goes onto the this like space we have. And moving on, this is base 2 representation of a mod 3 collab, so it doesn't really make that much sense, but I did it anyways to kind of just have a bit more comparisons. I'm gonna resize this and this. So yeah,
So okay, so you represented the same number in base two, or
this is
wait, hold
basically
on.
because no,
Uh,
this is the specific one we found in Stevens post, representing base 2. It
Yeah,
doesn't
but are
really
you
make a
starting
lot
with
of
the
sense to
same
plot
number
base
as that
2.
previous plot?
Yeah, yeah. We're starting with this number actually. Yeah,
Okay.
it's the same as the other plots.
Hmm.
Basically, I choose this so I can have like 2 clear points up here and then kind of see the behavior. And you can see that yeah, it does actually have a similar like patterns from the ones we have. They're just like mostly like for this representation, I just kind of want to see like what kind of like interesting like patterns or whatever like they could like could like expose like from different representations. And this one's the same. This one's actually, yeah, this is base 2, this is base 6,
Uh-huh.
this is also base 6. So basically, the only
But now this
place
one
that
does
has
converge. So what's the starting number for this one?
this one, you can see these 2 points, so it's the same as it's 2 to 100 and 2 to 70 because I'm only
Oh,
using
okay,
those 2
but the
points.
function changed, I guess. Is it?
Uh, yeah, this is a different one actually. I use a 4211, so I'm looking at one. This one basically like is a very convergent one I found. So I'm trying to see like the comparison between the neutral ones and a convergent ones.
What do you mean by
And
neutral?
the ones that like Steven found, basically that one's is a pretty neutral one. And I'm just kind of like these 2 sections, I'm just exploring like, what are the properties of the one he found, and I'm comparing with the ones that converges or diverges and seeing like
So
what's
I
the
mean, the
difference.
difference
So
between the special Collatz functions is, I guess, so like the one that doesn't converge, like this one, it's if it's 0 mod 3, then you divide by 3, and if it's 1 mod 3, you do 4n plus 2, and if it's 2 mod 3, you do 7n plus 1. And
yeah,
this that
and this
function
one,
is making a lot of things not converge, but that same number, this other rule where it's the main difference is in the only difference, yeah, it's in the third
yeah, yeah, and third
thing
thing,
there. So
yeah.
instead of multiplying by 7, instead of doing 7n plus 1 for the 2 mod 3 case, you do n plus 1.
Yeah, basically it just shrinks like the probability to go really high because 7 plus 1 makes a number like go really like large really quickly, right? So if something like that, it can definitely like lead to divergence. But this
Right.
basically just slows it down. So that's why it's like very convergent on the mod 3 space.
Yeah, I mean, I guess that's interesting. I mean, if you take something which is in mod three, which is three mod, which is two mod three, and you add one to it, then you're making it go to the zero mod three case, right? You're making it by adding one to something like that, you're making it divisible by three again, and so it's just sort of pushing it over to like the first case there, and then it'll be
Yeah,
divisible
right.
by three
Yeah.
later.
Yeah, so it'll just like more, this will be very convergent then, because like this basically pushes it towards here, and then this basically allows it to go like down really quickly.
Okay.
Yeah. So yeah, it's kind of interesting how these parameters actually interact with each other. I'm going to talk a bit more about that in this section, but
Okay.
um, as a conclusion for this exploration, like the digit representation part, um, I was hoping to see a bit more patterns, but the most interesting one I've seen is part of this one actually for the Collatz function. Um, I don't think I saw a parallel or like something similar to this huge triangle shapes in the other ones. So I guess the Collatz has something that's like really like unique, especially for this case. Actually, no, this is yeah, this is Collatz in base 3, yeah. So I guess there's something like pretty different for this and the one we're exploring from the last like section. In regarding to parameters, I think yeah we just briefly like mentioned about like how these can affect like convergence, how they can probably push it towards here. So basically, I need in order to explore like more, more of like generalized versions of class, I need to wait to validate parameter. Because early on, what I did is I tried to brute force it, and basically what happens is like I end up with a lot of like like invalid like sequences when I put into the when I put the coefficients into a function, and it's like a lot of it, so like I couldn't like justify like spending like put leaving the computer around in like 3 days and then actually like come back and look at the results, because like most of it's just gonna be junk, right? So here is me trying to find a way to parameter validate, but also I'm trying to find a way to basically kind of estimate like the likelihood of like this function being like oh convergence or divergence or neutral, right? Because if you're searching through like because we're basically here from now we're searching through a lot of like different functions in different mod spaces, and this will also make the process like faster because I can just look at the specific ones that being identified by this value function, and I can identify the properties of it. So but the issue is that this bias function isn't really like that coherent. It was more of like a judgmental or statistical inference I made, and then that's how I put it into here. It's a basically I took basically a bias function for the mod 2 space. Um, also compared it with the bias of the 3n plus 1. Basically, yeah, also compared with the specific collapse one, basically, and then I derived a generalized bias function based on experience and statistical arguments. It's not really like rigorous in the sense of mathematical rigorous and then like proving it. So
Okay, but
that could be
what does
something
the
that
bias
could be
mean?
considered. The bias.
Yeah, what does that mean?
Oh,
What is
basically
that
that
measuring?
means the likelihood it's going to go up or down. Basically, it's similar to ones that for the actual like original collapse, right? So if you have like a value that's like larger than 0 for the bias based on the parameters you put in, that means that it will be more likely to diverge. Consequently, if it's like a negative number, then it will be more likely to converge. And if we can basically with this kind of function expand it to the general space. I can basically just tell it to filter after I compute. I can filter out the results and find the ones that's closest to 0. And theoretically, these are the ones that's like the most neutral, right? It's not always
So
the case because there are
that
some
means what
outliers.
exactly? If it doesn't, if it's not trying to converge and be smaller, and the divergent ones are like trying to get bigger all the time, then it's like
Yeah.
if you find like a neutral Collatz function, then what does that mean?
If it's neutral, that means that I can, yeah, basically, I can show you this. My understanding, like neutral basically directs that like basically I think this is the most neutral one. Basically what happens here is that, basically you have a few ranges of values. But in the ideal case, right, everything you put into the collage should just end up in the loop on its own. So that means that it will just never go anywhere. It's gonna be a loop on its own. Right? It's not gonna like converge or diverge. So, but this is the one I found probably closest matches that definition of neutrality, where that you can see you have different like horizontal lines across, and that means that they converge just really fast. And a lot of them, it basically if you put in a number, it will be in its loop on its own. So basically, this means that it wouldn't like go anywhere because it's in the loop on its own, right?
Okay,
But
so well, that's
there's also
interesting. I
like,
mean, the original Collatz has like a loop down at like one goes to, you know, four goes to two goes to one, but like the whole, all the numbers go down to that root and get in that tail sequence basically. So you're saying for neutral, for this neutral type of Collatz function, like the idea is that there would be a lot of different separate loops
yeah,
in the
ideally
tree
like for
or when you sequence it. So like if you graphed the tree of it of where the numbers go, you'll get a lot of different a lot of different connected components that are different from each other, all going to like these loops.
Well, ideally, like if you have like a really neutral one, ideally it's gonna whatever value you put in, it's gonna be on loop on its own. And ideally, the values of the loop is gonna be like the variation between the loop, like values in the loop is gonna be small, right? So ideally, like you're gonna like whatever you put in is not gonna go anywhere. It's gonna be in the loop on its own, right? Because that would cause it to be the most neutral by the statistical argument side, and that's basically the hardest to prove because it basically doesn't like feel like a collapse anymore, but this is what neutrality is. So far, I don't think I've found one that's like exactly like that, but this one's the closest I've found. Um,
Well,
basically
yeah, I mean,
exists in
it's
the
gonna have
mods.
like at least a couple different numbers in that loop, but
Yeah,
I
yeah,
do. It's like
yeah, right,
if
yeah.
you're thinking about having a bunch of loops of various sizes, then it's like, okay, well, what are the range of sizes of the loops?
Yeah, right. So this is the most closest I found. Actually, it's in the mod 4 space. Do you note that I didn't explore like I explored from like 1 to 10 for mod numbers, but there's way more. But the issue is that as you go on, right, the more coefficients, the more mod numbers you have, the more like the more number of coefficients you have. So for Collatz, you have two. For mod 3, you have three. Mod 4 you get four, but as it goes on, like it's gonna expand like hugely. So it's gonna be like a computation time is gonna be exponential. So it'll be at some point it will just be like computation like infeasible to like actually like do it. So that's like another limitation of probably like with the exploration of like general collapses that you do have a limit upper limit of how many like mod spaces you can feasibly explore. It could also be down to how the method of generalization, like we do something different, and might allow you to do a bit more. But for the scope of this project, this is a limitation I have to work with. Now onto this one. I'm using a similar methodology with the graph I mentioned at the beginning, where I'm plotting a set of initial values, and I'm getting it by percentile and averaging it for the percentile. So as you can notice here, basically you have all of these like straight lines, and each of these lines would represent a specific loop on the percentile, right? So some of them has a bit more. You see for the 0.5 one, you actually have two of them. For the purple one, I think you have three, and some of them actually do overlap slightly. You can also see the brown one's actually pretty close, which is a bit interesting. But basically what happens is a lot of values you put in, it either converges really quickly to one of these loops, or it exists in one of these loops on its own. So if you look into the calculations I did, so there are ones that like look if you put in like I think
Okay, so yeah, here we have a loop going
yeah
two
this
three
one
eight two three eight. I don't know.
uh this one's the lower one. You can see on the lower bound here, it does actually converges really low. So up to probably like 1,000 something, it all converges down below 500, which is a pretty normal behavior for like some of the collats. But what I get interesting is as you get to the higher numbers, like larger values, let's say I put in like this is pretty much a very random number I put it in. Basically you can see that it literally just exists in the loop on its own. For this one, it also has the same behavior, and this loop is actually even shorter. It consists of only like three values, and then it just loops again. This one I think it's yeah, this one's also like three values actually, I think. Yeah. Wait, I think there's more. Never mind. But um, and same for this one. Basically, it also exists in the loop. But there are also ones that like kind of like break this illusion, especially in the larger number space, where example for this one, it converges to something that's still pretty large, but it's considerably like smaller than the initial value, right? So you can see some of the observation here where for the purple ones, you can see some of it goes to here, but like some of it like are up here. So there are some differences. So it's kind of interesting that this exists, but
Yeah,
yeah.
interesting.
Onto the what else to talk about? Yes, the bias like way of estimation. So I actually have to use the I actually do use the bias function to find this. So I explored the mod for space with like computation, and then I sorted the best one out using the bias. Now yeah, these ones are yeah, the bias is just mainly based on like statistical experience and stuff like that. I feel like more work should be done to actually like make this more solid, because sometimes it does have like some like extreme like sometimes the prediction is not gonna be exact. Like there are ones that like are just pretty like normal divergent or convergent like collapse, although they might seem like decently like neutral. So it's not perfect, but it does help tremendously on the exploration part. I think I also mentioned a way of parameter validation. Yeah, here. So this is another problem I have for searching through the large space. I think I mentioned that like you will get a lot of like invalid parameters. So what did I do is I found the relationship of the coefficients within a valid parameter. So you can see that it has to satisfy this kind of condition for it to actually be a valid like space. Because if not, like it will have like basically like one coefficient could produce some invalid like operation where it becomes instead of being an integer, it became like a float or something, and then that would basically that'll render this entire like collapse and invalid, because we're looking only at integer collapse. We're not looking at the other ones. There are also negative ones. There might also be like complex ones, but those are not in the scope of this project. So this is what I'm trying to do to figure it out. And this is here this in a mathematical function, which I use to find all these. And yeah, so let's look at some of the results from that exploration. So like I mentioned, this is one. I think this is the most useful one we found so far. But there are also other interesting ones. For example, this one. This is in mod 3. So instead of this one does -1 with -1 instead of +1. And you have a lot of like these like huge loops actually. You see here, there are some huge loops here, but compared to this, it's actually kind of like minuscule, because you can see that for the central part, basically it follows this kind of like it falls between the like a huge magnitude of numbers.
This is very interesting. So it looks like those. It looks like it's looping, and it looks like
Yeah,
those loops are about like 500 uh long. Like have a
it's
periodicity of
really
500.
big. Like
Uh-huh.
the loop here is like really big, like in terms of magnitude of numbers, and also the steps, right? Like it takes a few hundred steps to like complete like just one loop, right? As you can see, also like these are the normal ones. The behavior like for the up to like zero point 0.4 to zero point 0.1, these are pretty normal. They converges and they just stay flat for the loop. But these ones, the middle ones, are the ones that are like really interesting. So I think it's from yeah 0.5 to 0.8 percentiles. These are interesting. If you go higher, you just run into the influence of like divergent collapse, right? Basically, you have some of these initial values like just diverges, and basically that would alter the loop like by a lot.
Well, yeah. I
I
mean,
think also
either that will eventually diverge, but it looks like it's not getting bigger. That's the thing about it. So
Yeah,
if
yeah,
it's bounded, then it'll loop eventually.
yeah, right?
Just might
So
be that it'll
this,
be a very long loop.
yeah, right, this could also be a very long loop, but I'm more inclined to think that because I think for this one specifically, I did actually found some that diverges as well. So you can see in this plot where you can see these values, and I think these ones are the divergent ones. So there are divergent ones in here because this is a close to neutral one that's basically exhibiting the similar behavior than to the one that Stephen found in terms of divergence, right? So I suspect that for the larger ones, there's definitely some influence by the divergent, like, sequences, because like the probability is going to be higher as you go higher with the larger magnitude. But I think specifically this one, interesting part is I don't think the influences start like that. Like, I think the influences are pretty minuscule. It's before you like get to the top. Like for that one, actually the influence is pretty uniform. But this one, the influences from the divergent sequences is actually they only kind of starts to show when it reaches the top. So I found that this is kind of like interesting. So this would probably suggest that the distribution of the you know divergent class will be like there's going to be very little on the bottom parts, but there's going to be a lot more on the top, which is like really like a lot less uniform than what Stephen had found. And yeah, you can also tell by this. Basically, you can see there's like huge gaps between these divergent values. And for this entire like 1,000 like value space, there's like only three, I think. And also like these are the really huge outliers. The other ones are much more uniform down here. You can see like these ones are on 10 to 15, and you can see these clearly like these very like there's like a uniform two lines of and two clusters of the convergence. So it's kind of like it has a lot of similar behaviors to the ones that like Steven found, but also like it's also kind of like different actually because it's a lot more like it's like the convergent values are more uniform in the sense that they're converging at similar like spaces, but also you also get like higher extremes. So in a sense like that one would be more extreme than this one. And yeah, we talked about this one. I think this is another one I found that has similar behavior to this actually.
Yeah,
Um,
it looks like it's very neutral and that things converge very quickly to small loops.
yeah, it has the similar behavior to this, and the parameters is actually like it's not it's a bit different actually. So it's actually instead of like having like additive constant, it's gone. This is just basically for n. This is and there's actually two ANs. I don't know if that's like like actually valid for Collatz, um
What? So
but
this is
if
mod
you put
four,
like
and if it's
so
two or
basically you have
three
two
mod
chances
four,
of
you do 8n plus 0.
yeah, basically you have two chances of like 8n. So basically this just basically weights this like 50% chance like more,
Yeah, it's a
and then
function, a
these ones are
perfectly
just
valid function.
yeah, it's a valid function definitely. So basically this is what allows it. Basically theoretically you have more like I think like divergence, but I don't think that's the case because like basically if it's mod 4 you're gonna if you have like times 8 or something like it eventually goes to here and then converges. So
Yeah,
it has a pretty similar behavior. You can see it loops down here for the bottom 10%. Here for these ones. Um, and towards the top, we can see the same distribution of these three purple lines where they kind of like actually have kind of like a large difference. So kind of like corresponds to it well. The main interesting part, I think, for this one is that if you look at the graph like Cliff, like you can see these ones, they're not the middle ones are not that uniform, but you can see these ones, the leaps are pretty close together. So I think that these ones are a lot more uniform than this in terms of the convergence. And here, yeah, here's some of the estimation of the bias. But this basically also demonstrates kind of like another like issue with the bias like function where like sometimes it just predicts like 0 apparently, and then it's not really like well I mean it's close, but I'm guessing there's some limitation on like the digits, or it could be some limitations of the method I'm using. But yeah, just another kind of like show that like it's not like it needs a bit more work before it'll be like a really like a sophisticated bias estimation function. I also observed some general like trends between like the mod numbers. So, because like basically if you have different mod numbers, you have different chances and ways of being convergence or divergence, and there are some like interesting patterns from it. So basically for these ones, I'm basically using the bias function to kind of show the values, because it's basically the easiest way of doing it, and it allows me to sort through it pretty quickly. So you can see that for the mod 5 space, and this one is, yeah, I think this one is actually, yeah, one is mod 5, one is mod 6, and even I think the even ones actually no, this is mod 4. This is wrong. I need to fix it, but this is mod 4. Basically you have 4 parameters and this is 5. And you can see it for the even ones, you have these 0 prediction ones. And the 0 prediction ones I think specifically refers to these kind of like, you know, behaviors,
Yeah, the
in the sense
balanced
that they're
ones. Yeah,
very neutral. Yeah,
the
yeah, they're
neutral.
very neutral, right? And these I think only exist in the even mod spaces. The odd ones don't. They have really close ones, but they more generally behave like this. Like the ones that you have found, like in mod 3,
And
right?
how does that function
So
work? It does like empirical testing and kind of um, spits out those results.
oh, you mean the divergent param one?
Yeah.
Oh, this? Basically it nets a there's a lot of like because I use parallel map to kind of like do it, so like it's kind of like a nesting
I
nest,
guess
but
it comes down to what Collatz bias is doing.
Collatz bias is the bias function I defined earlier. I don't, yeah, we're not using this because this one's also a bit like weird and it doesn't really. Basically for this one, actually, yeah, I should actually talk about it, skip this, but this is basically another version of bias where I'm also trying to factor in the additive, the additive constant, right? Because you can see there's one on the edge. The original bias function only takes in the coefficients,
I see.
the A1 and A2, but it doesn't take in the constants. But the constants do also have like a huge effect on like, you know, the behavior. Like sometimes like we do +1 or -1, and it changes behavior completely. So I tried to do it here, but it just doesn't really work out, and a lot of times it contradicts itself. So that's why for some explorations I switched to this one. So basically it's basically using this function. You have a coefficients and you have the basically the length of coefficients is also just the mod number, right? Because how many coefficients you have corresponds to how many like the number of mods you have. So basically does the log 2 of that, and then you pass the coefficient in as a list of values, and that's how you get like an estimation based on the bias. It's pretty similar to the ones that, you know, for the it's pretty similar to the ones for the original Collatz-Type that's being provided.
Got it. Got it.
And yeah, we're almost done. Yeah, you can see these differences where for the even ones you do have like that behavior. Now that's another issue with the with the bias estimation, is that sometimes this is from mod 3. It estimates the zeros, right? You can see. So theoretically it should have the same you know, you should have the same behavior as this one, but it doesn't. So
Oh, that's interesting.
that's another, yeah, that's like one thing I do actually kind of want to look into, where is there a way to like make the bias function even more sophisticated or better? Because there are cases where it does actually just contradicts, but in general it follows the same, like it does provide like a lot, it filters out a lot of the irrelevant results. So yeah, I feel like there's some edge cases that I think I didn't account for, or some like, you know, conditions I didn't account for in the bias function derivation, but yeah, due to the scope of like WSS, like I wasn't able to do it like fully.
Okay.
But yeah,
So what is this plot down here?
this one, I think this one is 17788. This is a mod 5 space one. Um, I think, let me check. Uh, yeah, it's basically this one. It's just showing that, like, from mod 5, the closest one, theoretically, is this kind of behavior, which is the same as the mod 3 ones. So basically, it kind of shows basically it kind of shows that for the odd mod numbers, you have these kind of behaviors. For the even ones, the best you can have could be these ones where it just like there's multiple, like there's a lot more like loops that you can end up into.
So what
Yeah.
does 17788 mean? I mean, is that
Uh.
those are the coefficients, the multi, is
Yeah.
that
Yeah.
specifying the rule?
That's the okay. That's the multiplicative coefficient. So basically, this is like one like 1 n plus like 0 or something like. This is and this also contains the division, right? This is 7 n plus like 0. This is like 7. Basically, it's
Yeah,
the
yeah.
first
So it's
like
like it's
7
one
n or something.
and that gets if it's divisible by 5, it's you divide by 5. Otherwise, it's like 7n plus something, and then 7n plus something, and then 8n plus something, and 8n plus something. Oh, I guess we're
Yeah,
not
right.
sure what
Yeah,
the
we're not sure what
what
the
those.
plus is because
Okay,
yeah, because we didn't factor in this bias function specifically. Because I did try it, but like it didn't work, like I mentioned. So
but whatever this
uh,
rule is, those are the coefficients for it, and it's mod 5, and it looks like
yeah,
things converge eventually to whatever loop that they're
yeah,
going to end up in.
yeah. But it does have a similar behavior to what Steven found here. But I think this one converges a bit more aggressively. Like for that one, I think you have to go out to like pretty far to actually see the convergence. But those actually converge. But these ones, you can see that all the statistically on average converges pretty much between like 2,000 steps here actually. Yeah, about 2,000 steps, which is like a lot faster than what Steven's function had.
So this would have a
But
negative bias, do you think?
yeah, that would
I mean, is
theoretically
that
have a
what the
negative
bias
bias.
function told us?
But well, here's the thing, because since it does actually have divergent values, I want to say that would be a complete negative bias.
Well, no, the
So
17788
no, it
is
doesn't actually show
up there.
it's
It
negative.
has.
I think it's a really small positive divergence.
Oh, it says it. Okay.
Yeah, because I think I'm mainly looking. Yeah, because basically what happens is like they're definitely like slight divergence onto it. Because like I said, there's a really divergent sequence in these kind of functions, like we explored in Stevens function. So yeah, these are some of the interesting callouts like specific functions I found. Um, Like I think like in conclusion, this probably is the most neutral one I found so far. There might be more, and there might be like different ways of finding it, but due to the scope of the project, this is how much I was able to explore. I want to thank all the people who have helped me on this project, especially to Stephen Wolfram for suggesting this project and my mentors and TAs, and especially for Dugan for giving me this opportunity to present on the Wolfram Institute.
Very cool. Thank you for coming on. Um, yeah, I guess some interesting things to explore. In case people want to explore more in this topic, it's a very interesting topic. Basically, uh, there are a lot of variants of the Collatz function to explore, and then like looking at the biases, looking at like particularly neutral bias functions. The question for me that I have in mind is like, okay, you want to look at these loops that things start circling in. How big are the loops, and how many are there? Like, would you suspect that there are going to be infinitely many loops for a function of that's neutrally biased?
Well, ideally, like I said, like yeah, it would be like infinite many loops corresponding to many values, right? Because ideally, like as soon you have that initial value, it ends up in a loop on its including its own, and that means that statistically it's gonna be staying neutral. It doesn't go up or down because it has that loop already. So that would be like the most neutral one, but um But theoretically, that also kind of like contradicts some of the behavioral like characteristic of Collatz, right? Because like for Collatz, you do have some kind of random walk, and it shouldn't be like set in stone. So so we can only I think that I think it's more probable that we can only have like something that's infinitely close to it, but it's not going to be exactly like that.
Well, yeah, it's not really a random walk because it's like it's deterministic, but on the outset,
Yeah,
it's
yeah, yeah,
computationally irreducible in the sense that you can't like
yeah, yeah,
predict
yeah, yeah,
everything. Um,
yeah, yeah, yeah.
but yeah, so and then for ones of negative bias, ones that kind of everything kind of goes down in value, it's still the case that like you might have a finite set of loops. So you might have like a disconnected graph when you plot out like the nest graph of all these things.
You mean for convergent ones?
Yeah, for convergent ones.
Actually, for convergent one, you wouldn't like. Do you mean you would see this kind of behavior, like different types of loops, like this kind of behavior, or do you think? Well, for the convergent ones, if there's gonna be many loops, then you're gonna see a straight down, and then it's gonna be like more like a flat line. It's not gonna show this behavior because what happens here is that you get some of these divergent sequence mixed into the average, and that's contributing to its like increase. But
Well,
for
I mean,
a
here
for a
it's like
negative,
you have convergence to these loops that are like on the horizontal bars, right? You get down to like a finite
yeah, yeah.
sequence that loops, but then you have like this tributary that like this big number gets bigger, then it goes smaller, then it goes into one of those loops.
Yeah, right, yeah.
And
What's your
so
question then?
I guess like here, are there going to be infinitely many loops, or are they going to be, is it possible to have finitely many loops, but still have everything like be convergent to them?
So do you mean so in the negative bias sense then, like
Yeah,
convergent sense?
yeah,
Um, well, in the convergent sense, it is probably possible to have multiple loops, but you wouldn't see like any like sort of like behaviors that like goes like really up, and then I mean you could potentially see this, but it would be more like definite, and then it wouldn't have like these kind of like like I guess you would, but it wouldn't be like this increase that much because like basically statistically speaking, it would always converge. It would pretty much just assuming like it will always converge, right? If you have a negative bias, it simply always converges. This is what I found. I don't think I wrote it in here
yeah.
actually.
I mean, that's
Probably
the
in the
idea. It's
minutes.
like
Yeah.
if it's biased downwards, then like on average, the size of a number will decrease.
Yeah, right. So that means that it wouldn't have a divergent sequence in it. So it would be more just like going straight down and converges to some value, like
Right,
some straight
right.
line
And if
here.
it converges to some value, then if it converges to lower values, then you have a probability that it'll go into a loop. I guess. I mean, that's the
Yeah, yeah,
conjecture,
yeah.
right? I mean, it's just something to
That's the
think about.
conjecture, pretty much like yeah, because for all of these values, if it has a negative value, it should eventually converge to something, right? A loop or something, right? That's basically expansion of whatever the Collatz conjecture is.
Um, right, right. And then whether or not it converges to a finite number of loops or infinitely many, I guess is a different question.
Yeah, yeah. That could be another like question to explore, but yeah, the scope of this project was definitely not like to explore that. So
Of course, yeah. I mean, it did a lot in 2 3 weeks. Of course, like this is
yeah,
open problems in mathematics. Like you could make careers out of this kind of stuff.
I mean, yeah, it is
Um,
an interesting problem, but it's also one of those problems where like like you might spend like your lifetime like like solving it and probably never do that. So
I mean, also it's generally advised not to go into this sort of problem for like a PhD or something because it's too big
yeah, yeah, right.
of a
It's too
problem. But
big. Like you can't.
there are plenty of patterns that are like exhibited and plenty of stuff to explore, and it's super interesting.
Yeah, there's definitely a lot of like super interesting behavior on it.
Uh, question. So, since the project is talking about Collatz conjecture, I don't know if you're familiar with this problem, basic beaver problem that explores, especially basic beaver 6, which is mentioned to like it's mentioned that the Collatz conjecture needs to be solved for this problem to be solved. And I was curious if you're familiar with this, and is it a connection that you can also point out, because it's not so obvious to me, the connection between Collatz conjecture and the busy beaver problem. Let me just paste the link on the chat. But if in any case you are familiar with this, is there any connection to this problem and what you are doing right now in Collatz conjecture?
So are you asking
'Cause
about the
I see a
connection?
mention of I see
Sorry.
the Collatz, no, the connection between Collatz. Like, what are you searching for in the Collatz, and is it something that can be understood in the problem of busy beaver, where it's like kind of searching of something, yes, but it's not obvious to me. That's why I'm asking if there is any connection to the conjecture that you're talking about, the Collatz, and this problem that I shared, because I see the mention of 3n plus 1. And I guess that's what we've been exploring in the conjecture. And also like the evenness and the oddness of each function.
Yeah, I'm not too familiar with the busy beaver and the challenge, like not too familiar with that. Are you
Right.
asking?
So yeah, I was curious if like what is being searched in the conjecture, like the Collatz conjecture. So you've explored all this divergence and convergence, and I'm curious, what is it that you're looking for in this exploration?
Oh, you mean the goal of this project?
Not not the goal, but like the conjecture itself.
So the relation to the Collatz conjecture, is that what you're asking?
Yep. Yes.
Oh, okay. Well, this one doesn't really have that much direct connection to whatever Collatz is, but basically, theoretically, if you have a pretty biased like function, right, it would be the hardest to prove, because basically it doesn't exhibit all the behaviors that you see in the Collatz. So basically, it would just be looking like that, and then, I mean, yeah. So it doesn't really like basically it's not going to be able to, you're not going to be able to prove it. So in terms of the relation to the actual Collatz conjecture, I don't think there's that many. Obviously we do use the original Collatz, but I think this is like more of like a different problem. There could be some ways like how like the expression done here can be generalized on, because we're basically thinking of more generalized like version of Collatz. So if we can prove or find something on the more general version, maybe we can track it down and probably use it onto Collatz. But I don't think there's like too many of direct connection to the original Collatz conjecture.
Right. Okay. I see. But the exploration is kind of the same, right? Like you're looking for patterns or convergence and divergence of functions, right?
Yeah, we're looking for like basically we're looking for that. But I mean for the Collatz like conjecture, right? That the issue is that basically the reason no one has been able to prove it is that basically if whatever you test it would be convergence, but there's also no way of actually like have a systematic proof of it. So basically yeah, that's Collatz. But for this one, since we're looking at a much greater variety of functions, we're basically looking at the more statistical behaviors of it. And instead of proving anything, we're pretty much looking at a more general trend that's being exhibited, because the scope of the also like the scope of WS limits like how much I can actually do. So pretty much just limit to more of the exploration side and looking at across the general trend. I mean, there's definitely like some components that could definitely be like applied to Collatz, the original Collatz conjecture, but yeah, like I said, it's probably not going to be like that, like useful at least like and if someone figure out something, that would be really cool. But at least in my understanding right now, yeah, I don't see that much of a connection.
Do you feel like we're any closer to solving Collatz?
You any closer to solving Collatz? Probably not, honestly.
Mostly
I think the
kidding.
close we probably have been like pretty close right now. Like we already have like pretty much like an almost proof from like Terrence Tao, I think like a few years ago. But I mean, it's just gonna be really hard for anyone to actually prove it. I mean, there's also the chance of disproving it, right? Like you find one that's like divergence, right? Like how we found in that like Stevens function and the other
Well, not
function.
even a
It exists,
divergence.
like,
If you found a number that like went down to a different loop that was different from the
oh yeah, that
one
could
four
also be
two
a
loop.
thing. Yeah, right.
Uh-huh.
Yeah, but there's no way of like because the issue here is like there's not really a way to generalize this kind of behavior and then like probably apply it to Collatz. Right? We can see for some of them it does have it, but there's just no way of knowing if Collatz would have it. Like that's a little that's the main issue here because the variations do like a lot of them do have different behaviors and some of them have many loops, like a lot of loops. Some of them have no loops, some of them have like one or like two or few, and each also have a different behavior, right? Right, we just don't know if this is the case, right? There could be a case where maybe like Collatz, since Collatz is pretty like convergent, there might be a case where it's like, but theoretically, right? Because um, I mean, right now we're all assuming like convergence. If you have a convergent like bias, you pretty much have to like to go down there, and so far the behavior is solid like that. But maybe if you find like one within the convergence space where like you found one that diverges, then maybe that connects to Collatz and maybe allow like people to disprove it. Like that could be a case of doing it. But right now, this isn't like really in the scope of this project, so I didn't do that much exploration on that.
Can
I
you
mean,
scroll up
like,
to the one
yeah.
that had the longest loops?
The longest loop, yeah,
Yeah,
this one,
that
I
one.
think.
Yeah, that's pretty cool.
Yeah, right. There's like, yeah, I mean, like I'm thinking about it as well, like, because the divergent ones, basically they have like, they have both like, convergence and divergence initial value. So maybe if you can generalize this behavior, maybe you can generalize to all of like, the functions have this kind of behavior, but there's just no way of knowing it. Like maybe eventually there will be a divergent or like, it converges to a different number, but we just don't know.
Wonder what these loops look like and how long they are. Uh,
Yeah, I don't think
this
that
is for a mod
the
3 case. Yeah, 4, -1, 7,
yeah,
4.
yeah, mod 3.
Uh-huh. Lot to explore.
Yeah, there's a lot of interesting behavior, and there's a lot of ones that I couldn't quite explain, and probably I don't know if anyone would be able to do it.
Are there any more questions, Nick, Brian?
No, I'm good.
Yeah. Okay.
Oh.
All right, Steve. Thank you so much for coming on, and thanks for everyone for tuning in. We'll see you again next time.
Thank you for this.